Hi everyone, and welcome to the session. Thank you very much for coming. I appreciate it's the last day of the conference, and it is lunchtime too, so I double appreciate your being here today. My name is Dimitri, and to give you a bit of an idea of my background, I spent 20 years at various service providers, internet service providers, carriers, and whatnot, so please take into consideration the professional deformation that comes with that. So I'm here to talk about troubleshooting of NSX and basically just give you kind of a overall framework for troubleshooting, disclaimers and whatnot. So what we're going to cover today is a common question that is asked, does network virtualization make fault finding harder? Does it complicate things? Does it multiply complexity or whatnot? What do I need to do to be good at fault finding and whatnot? And where do I need to look for troubleshooting? And I'll present a small walkthrough scenario. This slide deck is quite heavy on words on the slides, and it was on purpose. I do realize that it's often difficult to read and focus on what person is talking in front of you, but the slide deck is done that way so that you can take it after the session and basically use it as a reference at a later time for your quiet reading. So it's actually quite suitable to read without someone presenting. So if you see something that you think is very useful for you, don't spend too much time taking pictures or something like that. You will always have access to that later, and you can use it as a reference. Okay, first things first, show of hands. Who is using VPNs? Right, everyone is using VPNs, excellent. Who can explain how VPN works if a layman asks you? Like someone, okay, so not too many people, okay. So network virtualization is not new at all. The concept that network virtualization uses is exactly the same as is used behind most of the VPNs. So MPLS VPNs, carrier Ethernet VPNs, and IPsec, and we're talking about here IPsec, site-to-site VPNs. So the principle is that there is a common transport portion which is used as a resource pool for the VPN services. So this, you can actually think of it very similar as the server virtualization. So you have a server which is presenting resources to your virtual machines that consume those resources. It's a very similar concept with the VPNs. There's a transport portion of it, which is a connectivity resource pool, and then you have at the edges of that resource pool, you have endpoints which implement the actual services, which draw from that pool the actual connectivity and bandwidth and whatnot. So in the MPLS VPN case, MPLS transport network is the resource pool, and on top of it you have a variety of services like a layer 3 VPNs, layer 2 VPNs, or mix of thereabouts. With NSX, it's the same. It's in a very similar manner. We have IP transport network, and logical switching, routing, and security as other services that use that to provide the connectivity to your applications. Important point here is that with that separation of concern, transport network does not need to be aware of the services that ride on top. So essentially, when you have your traditional data center network with VLANs and everything, all the elements inside the data center are aware of the end application connectivity. So if you have VLAN segments for your applications, these VLANs are configured everywhere throughout your fabric, or at least to those sets of servers where these VMs need to live. So essentially, inside the physical network, you have exposed your application services so it's a throughout, from the edge throughout the network and to the average. With the VPNs only need to know the portion in the middle, the transport portion in the middle, only needs to know how to get between the edges of the network, but doesn't need to know about the services that riding on top. So it basically just gives you clear separation of concern in terms of the configuration and troubleshooting. So that's, as I just said, the separation of concern and troubleshooting is beneficial. Transport is simple because you don't need to carry the state for your end services inside the large network where there's lots of them, and the actual services are only configured at the endpoints of your transport network where it's necessary. So essentially, you're separating them and kind of putting them into compartments. I cannot pronounce that word, compartmentalizing. So since the transport is simple, it is easier to troubleshoot it as well. So it is all you need to do is validate whether the endpoints on your transport network can reach each other, and then you're pretty much good. And you can, from that point on, you can focus on the services themselves. For NSX, transport is IP connectivity between the VTAPs. So VTAPs is a virtual tunnel endpoints which do the encapsulation and decapsulation. I'll touch on that just in a second. And to validate the connectivity there, we can use it using the tools that are available on hypervisors called VMK ping. So NSX services. NSX includes two types of services, the integrated services and distributed services. So integrated services are provided by the Edge VM, so ESG, Edge Services Gateway. It's fairly easy to reason about that. It's basically like your physical router, but it's been taken out of a device and it's now sitting inside the VM. It's a virtual machine, it's got multiple interfaces, it does things to forward packets between those interfaces, or does the transformation of if it's necessary, like load balancing or NET or things like that. But distributed services are delivered in kernel over hypervisors, and they are, by nature of it, are distributed. They are like a single thing that you can touch and move around and whatnot. So for that point, we'll focus this session on the distributed services. What's the requirement for being effective at troubleshooting? So I like thinking of troubleshooting as knowing what the current state is and how it is reached. So when you're thinking, when something is not working, you need to kind of make a clear idea of what does it mean that it's not working. So when you say it's not working, you need to have a fairly good idea of what does it mean working, right? So, and that working, as I said, is a combination of the actual state and how that state was achieved. So we'll look at that at this combination for the logical switching. So let's another show of hands. How many of you can tell standard switch from a distributed switch on the vSphere? Okay, lots of people. Excellent. Which one of you spent more than a day with hands-on NSX? Excellent, excellent. And how many of you played around with logical switches in that time? Okay, beautiful. Tricky question. Who can tell me the difference between VXLAN, VNI, and logical switch? Okay, cool. I'm just trying to gauge the kind of a level of depth where I need to spend more time and where I not. Okay, so terminology for the logical switching. So VTAP is a tunnel endpoint. It's an IP interface, one or more IP interface that is created on your ESXi hosts, which do the encapsulation and decapsulation into VXLAN. That IP interface is connected to a VLAN or actually connected to a port group on your host, which is mapped to a VLAN on your physical infrastructure. And VTAPs, the rule of thumb that VTAPs need to be able to reach each other, right? So in your NSX installation, be it a single VC installation or it's a multi-VC installation in 6.2, all your VTAPs must be able to reach each other. Well, it's a fairly rough rule of thumb, but that's kind of an overarching thing. They need to, because that's how they communicate. Right? And the VTAP is the attachment point of your logical space where the services are to your physical space, which is your resource pool that we talked about, the IP network. Logical switch, also referred as VXLAN. Logical switches map to distributed port groups in vCenter. So if you have transport zone which covers more than one distributed switch, there will be a distributed port group in all the switches which are members of the transport zone. If you have a logical switch in a transport zone that covers one distributed switch, there will be one distributed port group that corresponds to the logical switch. So if you look in the vCenter server, obviously you see a DV port group, one or more, right? And if you look in NSX Manager Network and Security interface, you will see logical switches. But there's a very direct correlation there. VNI is the VXLAN network identifier. So each logical switch has got a VNI assigned to it. So VNI is the value which will be put into VXLAN frame to identify that VNI when the encapsulation and decapsulation happens. Okay? So each logical switch has got a unique VNI. Another way of looking at VTAPs is as cables, essentially, connecting your host local switch to other switches somewhere else. So for example, if you look at your physical switch fabric, so you have, say for example, four physical switches, right? And you have cables between those switches because you need for your data to pass between them. So when you look on your physical switch, you will see a potentially trunk interface which has got one or more VLANs on it, right? And you know that this interface is an interface where you will need to send frames that you don't know what to do with, right? So when you're dealing with destinations which are not locally known, you would need to forward those frames to these out of these ports so that the rest of your network can take it to their ultimate destination. So VTAPs serve the very similar function in a logical switching. So you can think of VTAPs as links to the other hosts in your infrastructure where there are interested parties that are connected to the same logical switch. Well, it will become clear a little bit later. So what is logical switching? Logical switching implements layer 2 connectivity on top of layer 3 IP transport. Right? vCenter, as I mentioned, sees logical switches as slightly special DV port groups. I will share with you what this slightly special thing is. And if logical switch spans multiple distributed switches, NSX Manager creates DV port group on each. And there's a little article that I wrote which goes into those, into background details on how the things work there, what's the relationship between the switches and transport zones and whatnot. DV port groups making up a logical switch have opaque attributes on them. What this means is that when the NSX Manager creates logical switch, and it creates the corresponding distributed port groups, it specifies a set of special attributes and gives them to the vCenter server. So when the vCenter server connects the virtual machines to that special DV port group, it will pass those special attributes so that the VXLAN infrastructure on the host sees those special attributes and knows what to do with that packet and do the special treatment for it. Yeah, you probably, those who have played with NSX, you probably do realize that only one distributed switch in your given cluster can be prepared for VXLAN. Okay. How logical switching forwarding works. So logical switching operates on per VNI. So like in the physical world, per VLAN, forwarding is per VLAN. So essentially, if you look at how forwarding is done within one VLAN, then you can explain how forwarding done is in any number of VLANs because it's basically the same. So inside each logical switch, LS is logical switch and VNI is, as we've mentioned, it's a synonym for the logical switch or VXLAN or VNI. The forwarding is the same. So the frame is received from the virtual machine by the vSwitch that sits in your ESXi host. And this switch then looks at the destination MAC address of that frame and makes a decision. Is it a local MAC frame? So do I know about that MAC frame, which is maybe on another virtual machine that runs on the same host? If it's not local, then I need to find where that MAC frame belongs, right? And to do that, it will need to find the VTAP IP address for the host where that MAC address lives. And once that process is done, once you found it, it will encapsulate that frame into VXLAN header, put it into IP packet, and send it to your physical network, and then it will make its way to its destination. I'm hoping that everyone is clear on what the local MACs means. It's basically when vCenter server creates a virtual machine, or when you create a virtual machine, the MAC address is assigned to virtual network cards for each VNIC on your VM. And when that VNIC is connected to a DV port group on a host, that MAC address is actually passed to the host. So it's vCenter server makes that MAC address known to the host. So the switch component on the ESXi host has a list of VMs. Has a list of MAC addresses which are local to that host, and it knows exactly if it sees a MAC address in a destination as a destination of a Ethernet frame, it would know if it's actually local, or if it can't find it, it's not local. Right, so for forwarding to work, logical switching needs to have answers to the following questions. Do I know the IP address of the VTAP where I need to send that frame? So if it already has that data, then it will do the encapsulation and send it off. And if it doesn't have that data, and it will need to send that frame to all the VTAPs on that logical switch and hope that it will find its destination. So if case B happened here, that it's not local, the question that it needs answer is, what is the list of those VTAPs that I need to send them to? Because remember, since VTAP is an IP, VTAPs are addressed by IP addresses. These IP addresses can be anywhere. So you need to be very specific which of these IP addresses I send things to. You cannot just flood. So you need to have an explicit list of these IP addresses to send to. So how do we find out? Switch the VXLAN module on the host keeps the table called VTAP table for each logical switch. So that VTAP table is built when, as the hosts get virtual machines connected to logical switches, and once the first virtual machine on a host connects to a particular logical switch, that host will join the VNI So the process of joining the VNI is essentially exchange of the data between the host and the controller, where the host tells the controller that it is now interested in this particular VNI and wants to be a member of that VNI community. Okay? I have a diagram with a walkthrough just on the next slide, which explains the process there. So once that first VM on a host connects to VNI, the host will inform the controller. Controller will give the host, if that host was not on the VNI before, so he doesn't know who else is on it, the controller will send it the list of who else is on that VNI and inform everyone else on that list about the new guy joining. So that's 3 hosts. Host 1, 2, 3. We have a logical switch with VNI 5000. Host 1 and host 2 have VM1 and VM2 connected to VNI. And underneath each host, you will see the VTAP table. So host 1 has VTAP 2 in its table. Host 2 has VTAP 1 in its table. And the controller knows about both host and 1 and 2. So now let's imagine that the host 3 would like to join the party and has a VM3 which is connecting to that logical switch. So the process is going to go something like that. Host 3 is going to inform the controller that it has something on VNI 5000 and would like to join that VNI. Controller will reply to it back saying, hey, there's 2 other hosts on that VNI and here's the VTAP IP addresses, and send it back. And at the same time, he will inform the host 1 and 2 about the new host arriving. So once that process is complete, each host will know about everyone else on that VNI. Okay, does that make sense? So if we have, for example, like 8 hosts or something like that, but only 3 hosts have VMs on that VNI, there's going to be still 3 entries in the VTAP table, not 8. Right? So that basically is very important when you're looking at the replication. So if host 1 sends a frame that ESXi host 1 doesn't know where to send, it's not going to send it to all 8 hosts. It's only going to send it to hosts 2 and 3, right? Because these are the only VTAPs that are in the table. That's why I said earlier that VTAPs are like cables to other hosts, right? So if there is no cable, you don't know where to send. Okay? So let's have a look at what these tables actually look like. So again, fairly complex drawing, but you'll basically can look at it later. So what I'm showing here, 2 hosts, 1 host, second host. There is a distributed vSwitch called Compute VDS, which is present on both hosts. We have a logical switch configured with VXLAN 10,000. There's 2 VMs on it. There's a web server 1, web server 2. If you played around with the hands-on labs, they will be familiar to you. They have their MAC addresses and whatnot. There is a particular VLAN idea on this host, which is used by the distributed port group for the VTAP. So there's a DV port group where the VTAP lives. That's a green one. And that VLAN is present on your physical infrastructure. So I'm drawing here a very simple case where both VTAPs are on the same VLAN, same subnet. But it is totally valid for them to be in a different IP subnets, and that can be a router, right? But the main point is that VTAPs IP addresses must be able to reach each other, right? Whether they are on the same VLAN, different VLANs, whatever, they need to reach each other. And VTAP is shown here encapsulating the red traffic coming from the DV port group and carrying it inside the VXLAN frames to the other side. Okay, so first things first, as we've said, remember I began it with explaining that we kind of have clear separation between the transport and the services. So first thing is to validate whether the transport is actually working. So we just we can do that by going logging into the shell on the SXI host and running vmk ping command. So command is vmk ping ++ netstack equals vxlan -d -s and so on. So the netstack vxlan, since NSX runs NSX. When it's installed, when you prepare hosts with NSX, it will create a additional IP net stack on your host. So it's a separate space like a VRF on your host. And this VTAP lives inside that VRF, so it has its own routing table and everything. So ++ net stack specifies that to run that ping inside that net stack. -d means do not fragment, so set the bit to not fragment. The point of that is to validate whether the infrastructure underneath actually supports MTU 1600 as per NSX installation requirements. -s 1572 basically says the size of the ping packet will be 1572, which is a payload. To that you add 20 bytes of the IP header and 8 bytes of ICMP, which will bring it to 1600 byte. So resulting packet size here is going to be 1600 byte. And IP address of the other VTAP. Okay? So ping successfully worked, so we're good. What did that mean? So if that ping worked, it basically proves that the required physical network connectivity works correctly. So that you've got the correct VLAN ID for your VTAP DB port group, that the VTAP IP address is correct, that netmask is correct, that VXLAN IP netstack gateway is correct, right? And the underlying switching or routing network is also correct. So VTAPs can talk to each other. Cool. What it doesn't check if your firewall is blocking VXLAN frames, because it's a ping, it's ICMP packets. You can still check that using traceflow tool. I'll show you a screenshot of what a traceflow looks like. So once we've done that, we can actually move on to troubleshooting our logical space. Oops, sorry. Somebody was trying to take a picture. Okay, so let's have a look at the VTAP tables. Remember, we had our nice little diagram with the controller having some VTAPs and hosts having some VTAPs. So let's have a look what does it look like. So in 6.2, we've added the centralized CLI NSX. So you can actually, you don't need to jump around the system to look at things most of the time. You can basically SSH into NSX Manager and run the commands to look at a variety of tables spread across your hosts and controllers and whatnot. So first command here is we have a look at the what do we have on the controllers. Because we had two hosts, we expect to see that controller VTAP table for VNI 10,000 will have two VTAPs. So we run the command show logical switch controller master. The word master means that go and figure out which of the three controllers is responsible for that VNI 10,000 automatically and query him instead of me going and figuring out and which one of you and giving IP address and whatnot. Very useful here. And ask about what? Ask about VTAP. So go and query master controller for VNI 10,000 and show me the VTAP table. That's what this command means. So what it returns the VNI 10,000 IP addresses of the VTAPs segment, which is essentially network address of the VTAP, which becomes important where we handle replication of the broadcast and non-multicast traffic. MAC address of the VTAP and the connection IDs, which I actually have a link to another blog post which talks about that as well. So output is healthy, so we actually see that both VTAPs are here. So if you see a VTAP missing from that and you were expecting to see it, there's a problem, right? So next thing is go and have a look, what do we see on the host? So on the host, we're expected to see on the host 1 should see host 2 should see host 1. So we go and say, show logical switch list VNI 10,000 hosts. Tell me which hosts have joined that VNI. So it says two host names and the host IDs there, which we will need to run the actual command. So host 34 corresponds to SX-compo 1A, which was on the initial picture. These are the, can't remember the name, or whatever it is. And second command basically says, go and query the host 34 for the VTAP table on the VNI 10,000. It comes back and says, yep, I have one VTAP, segment ID, VTAP IP, excellent. So it's the same information that we saw on the controls. And if we run it against host 35, we would expect to see the other way around as well. So VTAP's good. What about MAC addresses, right? So we know that the wiring is correct. Now, what about the MAC addresses? So, what happens when the VM gets connected to a logical switch? At that point, host on where that VM runs also reports that MAC address attachment to the controllers. So controllers will also have a complete list of MAC addresses of everything connected to the VNI. So in that step, we go and query the controller. Again, master controller for 10,000, but show us the MAC table. Yeah, good luck to me. And response comes back that we have two MAC addresses known to be connected to that VNI 10,000. And the VTAP IP addresses for these MAC addresses are as follows. So it's essentially if you know if the VM sends you a frame addressed to a particular MAC address, you look at your MAC table, and MAC table shows you that the VTAP IP address for that MAC table is blah. So that information is used then to create the VXLAN frame and pass it over. So let's go and have a look at what's the MAC with the MAC addresses on the hosts. So the command show logical switch hosts, host number VNI 10,000, and we kind of see that it's empty. So does that right or not right? Okay, it is right, because since there was no traffic, MAC tables have not initialized on the hosts. So the only table which is actively pushed by controls to the host is a VTAP table, right? Everything else is a kind of temporary information. It's a cached information. So the MAC addresses are cached, and if they are not used for a little while, they are basically aged out. So that's done because if the VM moves, then host doesn't try to reach it at the old location. And another reason for that is that logical switching is implemented in kernel. And we don't want to unnecessarily chew kernel memory space with all the tables, because there could be quite a lot of these MAC addresses in your network, right? And if we basically duplicate that information to every single host, it can contribute to a bit of memory chewed up. So essentially, it's not pushed proactively, it is on demand. Okay, so when the time comes to send something to a MAC, so a VM tries to communicate with another VM, it sends a frame, and the switch on the host receives that frame and has a look at it, looks at the MAC address, okay, I don't know, it's not local, I need to find out. And goes and queries the controller, and says, Mr. Controller, tell me, because I know that I've been told that you have a nice cache of the MAC addresses and VTAPs behind them. Can you tell me, what can you tell me about that one? So Mr. Controller goes and looks in his table and finds the corresponding entry and sends it back to the host, and now host knows the VTAP IP address, where to send it to, okay? There can be the cases where the MAC address is not known. For example, when your logical switch is bridged to a VLAN, right? And VLAN can be hosting things like physical servers, which don't really report to the controller, right? So it is entirely possible that controller may not know that information. So controller will reply back basically saying that FF, I do not know, right? So it's, the answer is here, but answer is useless, go and flood. So that's what the host will do, it will flood to all the VTAPs because he knows about them. So if we run a ping, right, so that's to initiate that process of the host going and querying the controllers and getting the information down, we will see the information gets populated on the host. So we will see the inner MAC, right? We will see the outer MAC. Outer MAC is the MAC address of the VTAP, and we will see the outer IP. So all the information in that table is used and useful to create the VXLAN frames to reach the other host. Okay, make sense? So good. So there's a trace flow tool that I've mentioned. Is a tool that allows you to visualize the path, data path that frame takes between endpoints. So what traceflow can do, you can do traceflow between virtual machines connected to the same logical switch, or between virtual machines connected to different logical switch with distributed logical router in between. If there is an edge gateway in between, it will not be able to do the end-to-end. It will stop at edge gateway because it leaves the kernel space, right? Because it's not really in kernel forwarding there. Basically, it's only can visualize in kernel operations. So what we see here is that once the frame is in, okay, so what does it do? It actually injects frame like it was sent by the source virtual NIC and extracts it just before it's delivered to the destination point. So essentially, it's a pretend traffic which is not seen by the source or destination virtual machine. But it looks like it was sent by that actual machine. And you can manipulate the advanced options. There's like IP, UDP, traffic type, and payload sizes, and you can actually put things into payload and whatever. So it's quite flexible in terms of what you can create to validate this function. And by the way, that will highlight if your firewall is blocking VXLAN traffic in between your hosts, it will actually fail because you will actually see where the failure is between the physical hosts. It will leave one physical host, but will never make it to the other one. So step 0 is injected into VNIC. Step 1, it's received by distributed firewall module. Step 2, it means that it passed the distributed firewall module according to the rules configured. If you had third-party integration, things like Palo Alto firewall, for example, configured as well as your distributed firewall, there will be 2 more firewall things received and forwarded. But you will not see what happened inside Palo Alto thing. But you will actually see that the process, it will be received, forwarded, firewall, 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 firewall. Right? So at least you can actually see that, yes, it has been passed over to the third-party solution, and it has been received back. Once that is done, it's forwarded out out of your source host, has been received at the destination host, and it's passed in and out of the distributed firewall on the way to the destination VM. Okay, so what we talked about so far. Per VNI VTAP tables tells you what other hosts are on that VNI. Controller does maintain the VTAP table for all the okay. If host has no entry, it will query the controller. If controller has no answer, it will respond so, and so on and so forth. There's a blog post if you fighting the jet lag and whatnot will help you. Okay, so that is the what we looked at is the current state. So we looked at how the forwarding works, and the forwarding works based on the state that sits in the host, right? It's a distributed state that sits in the host, and we had this distributed state is our VTAP tables and MAC tables. So the second part of that question is how did that distributed state actually happen on the hosts, right? So let's have a look at that, because if you see that forwarding is not happening and you look at the distributed state and it's wrong, so where do you look and how do you find out where did it go wrong, like what might have happened? So quick background on the logical switch creation. So when you create a logical switch, NSX Manager allocates the VNI. It's got the pool that you've configured there, the segment IDs. You say like segment IDs from 5,000 to 10,000 or something like that. So go into that segment pool, grab the next one, allocate a multicast IP address if your logical switch was of type hybrid or multicast. Right, we'll create a DV port groups on the VC and give them the multicast IP address and the segment ID or VNI as part of the creation of these distributed port groups. They are passed as a special opaque attributes. Next thing, it will tell the controller cluster about the new logical switch, saying, hey, be prepared to handle queries for that logical switch. And DC now has those opaque attributes, which it will use when it's time to connect the virtual machine to that logical switch. Okay? So a bit of a diagram there. So first, user sends a query to NSX Manager to create a new logical switch. So that path can be directly via API. So if you have an I don't know, higher level management system of some description which directly sends API calls onto an NSX Manager. It will talk direct. If it's via UI, you talk to the vSphere web UI, and it's in the background, it does the same thing. It basically sends API call to an NSX Manager. NSX Manager talks to the center server, tells it here's new DV port group, here's VNI ID, here's multicast IP, and at the same time goes to control and say, hey, new logical switch. Second part is when you attach something to a logical switch. Yes? Here or here? Here. Right. vCenter is involved because vCenter is the guy who handles, okay, question is why vCenter is involved. vCenter is the guy who connects the virtual machines to logical switches. So it needs to have that information in form of the opaque attributes. Make sense? So for it to have the opaque attributes, it needs to be told what those opaque attributes should be. Yes? Okay. So step 2, if we go and connect the virtual machine to a logical switch, we talk to the vCenter server for that, right? Saying, vCenter server, connect me this particular logical switch VM to a DV port group or to a logical switch. vCenter server goes and finds the host where the stuff is running and creates the new distributed port and passes the opaque attributes along with that creation of a distributed port. So host now has those opaque attributes allocated with that, associated with that distributed port. Once that's done, host is going to go and join the VNI and get the other VTAPs on that VNI and send also a notification of the MAC of the VM1, basically saying that VM1's MAC address and it's now connected to VNI XXX. Okay, we see here controller interaction. Which one of you can tell me how host did learn about the IP address of the controller? How did host knows where to find the controller? Hands up. Okay, cool. For those who didn't raise hands, here's how it's happened. So, list of the controllers and their SSL certificate thumbprints for because there's the host to controller communication is encrypted with SSL. So we need a way to ensuring that they're actually using the correct certificates. So they exchange certificate thumbprints. are passed to the host by NSX Manager. First host picks one controller at random, right? One host boots up first time. It will pick one of the controllers and connect to it and get the list called slicing table. In slicing table, it's got the following information. It basically says, controller this is looking after these VNIs and these distributed routers. Controller 2 looks after these VNIs and these distributed routers, and so on. And so when it has something on a particular VNI, it will know directly which of the 3 controllers it needs to talk to. Okay? That information that it's got is stored in a config by VSM file, and it's fairly straightforward there. I'll show you on the next slide what it looks like. And there's a command there, and in that file you will see that the port, the TCP port 1234 for the controller. You will see the IP address of the controller. You will see that its communication between the host and controller is SSL encrypted. Thumbprint for that particular controller, and that's about it. And you have that section repeat for the 3 controllers. We keep on talking about those opaque attributes. So what do they look like? So here's one way to do this. So first you can find out your port number, so like ephemeral port number for your VM's VNIC. So do the netstats -l. It's going to show you the port number. So your client name is web server ETH0, and you get that port number, and then you go and look at NetDVS, and that's this grep thing is basically go look for the port number and step back 30 lines, and then look for word VXLAN in it. So if you just do the NetDVS -l and less or something like that, and you can just look for that thing, and there's a whole bunch of information about that port. And in that information, you will see these 3 things. There's a VXLAN control plane. One stands for control plane is enabled. Control plane is enabled for logical switches in hybrid and unicast mode. Okay, for multicast, it's going to be disabled. You will see the in hex represent your VXLAN ID, and you will see multicast IP address. And if it's 1, it means unicast. If it's not 1, there's going to be a multicast thing there. And it's a way to actually convert hex into the deck there. So to pull it all together, with a lot of things talk to a lot of things. So like a little of a reference diagram. So user talks to API manager and vCenter server. NSX manager talks to all hosts, to all controllers and vCenter server. And vCenter server talks to all hosts, and control node also talks to all hosts. We have a nice document published on the communities, which describes all the necessary firewall rules, and basically lists who talks to whom on what protocols and ports and things like that, so that you can configure your underlying infrastructure correctly, so nothing is blocked and everything is working as expected. Okay. So very quick recap. So you hit an issue with the logical switches 1, 2, 3, 4. What's the process to follow? So first thing you check is whether the communication channels are up or not. Remember that little diagram with things talking to each other? We have 3 things: the NSX manager to firewall agent, essentially it's NSX manager to host, NSX manager to control plane agent, it's the NSX manager through firewall agent to the control plane agent. They are kind of a little bit of a daisy chained, a little bit. And the control plane agent to controller, whether the host actually can talk to the controller. If you can see everything is up, we're good. If you see them not up, so if your NSX manager to firewall or control plane agent is not up, then most likely thing is that either firewall is blocking the TCP 5671, yep, or there's IP misconfiguration. And same thing with the other one. It's either TCP 1234 between the host and controller, or potentially a misconfiguration. So once you've got that out of the way, next thing is validate whether your VXLAN infrastructure is configured correctly. Best command for that is to show logical switch host ID verbose. It will show you quite a lot of info, including whether the MTU setting is correct, which it should be 1600 or more, what your VTEPs or VTEPs are configured, forward, like what the IP masks, gateways, and stuff like that. And it's also going to show you all the VXLAN networks that the hostess knows about. One thing is, for example, you have your infrastructure, you have like 10 logical switches there. You go on a host, you run that command, and it just shows you 3 VXLANs on that host. You go on scratch, something broken or not. These VXLANs will only appear on the host once you have something connected to that VXLAN on the host. Remember that. So if you don't see your logical switch listed in there on a particular host, it doesn't mean that things are broken. It means that potentially you don't have, that host is not interested in that VNI because it doesn't have anything on it. Okay? So once that is good, or if there is something wrong, you go and rectify and find out what misconfiguration might have happened. Make sure that all the firewall in the physical network is done, and as per that hardening guide that I've linked to. So next thing is to validate whether are things plugged in. So we know that the configuration, there's no user error, right? So we've configured everything's good. So our things are plugged in. So plugged in as is their connectivity. So first thing for transport, we go and ping the VTAPs, right? Can we ping between VTAPs? If you can't, obviously the communication is not going to work. If you can, then you can potentially run the trace flow and see for like making double sure that it's good or not. And for services, you do the trace flow. You can do the check the opaque attributes, which is going to tell you that the association is correct between the VM and a logical switch. So you got the right VNI ID, you've got the correct multicast IP address if it's a hybrid or multicast. This is kind of wiring thing. And if that is good, do a trace flow, and trace flow is going to show you where the things break. So a bit of a takeaways here. There's no magic, right? So there's no smoke and mirrors. We're very open about how things work, and it is in our best interest for you to understand how things work, so that you can be very effective with running your infrastructure and whatnot. We have all the tools that are necessary to look at how things work, and we also have a forthcoming troubleshooting course, which pretty much takes what I've covered today, but it's across the whole system, and it goes like a couple levels deeper than that. So that's, I guess, is pretty much all. And question time. We have microphone, or I can repeat things. Anyone? Questions? No? Everyone is hungry and happy?
Thanks. Is there a way to do a sanity test in terms of the GUI, the application, in the vCenter or at the NSX Manager, in order to determine if there is one pair in the network that doesn't communicate in one click, and then to drill down using the expensive and fashion tools?
I guess best way would be to use trace flow. Trace flow should actually bring you very close to a place where the things break, and armed with the understanding that I've explained, this probably will be will narrow down to where.
This is a narrow down, but I'm looking about you are building a network, a fabric with a cloud, with many nodes, many VMs, and yep. you want to determine if they are all communicated with each other within, let's say, VXLAN, okay, VXLAN 1. And then to drill down with the trace flow, right?
Well, there is no built-in tool that validates that all the time and basically says, oh, okay, I just lost connectivity to a particular VM. So my colleague Amol is here, who is looking after the, who can hopefully
yeah, so typically when you talk about applications, right, you'll have monitoring tools that you would use to monitor your health of the applications, right? So that application will typically give you an indication that something's broken. Now you have multiple paths between two VMs, that's great. If you don't, you need to know how things are. I think having if a network is broken doesn't mean the application is broken because there could be multiple paths, right? So the application actually giving you indication that it's broken, and there are tools that you can do, agents and stuff that are monitoring it. And we have tools like VROps, vRealize operations, which will show you the health of the network. So that will also give you an indication whether there is connectivity from point A to point B, those kind of things, right? So those are things that you will rely on primarily as part of the monitoring activity. And then this session covers specifically troubleshooting. So once you know things are not working, then you need to start digging deeper into where to fix things. And for those things, you need to understand the inner workings of the system, how things are working, what to look for, which tables to look for, what are the commands to use for those, and then narrow it down to where to fix. Because as part of troubleshooting, you need to know what to fix and where to fix, right? So those are the things that we are looking at here. But from an application perspective, I would say it's a much higher level where the application itself should have some indication whether it's broken or not. You'll have monitoring tools, maybe SolarWinds or some kind of tool which is polling the application, checking whether the health of the application is good or not, those kind of things, right?
Anyone else? Yep.
Yes, does Traceflow work with third-party tools like checkpoints, F5, and also?
Okay.
So no, it does not work with checkpoint because the way we have implemented and Traceflow is there are some tags or metadata that goes along with the packet, and those are not passed on to the third-party services. So once the packet has gone into the third-party services, we lose the context around that. So it doesn't report back.
You'll see that it's been forwarded to a third party and it's been returned from third party, but what happened inside third party you won't be able to see. If it makes
Typically, we'll rely on their logging mechanism like Palo Alto or whatever third-party checkpoint you're running, then they would be reporting their own action that they took on the packet to their own console, like Panorama or Checkpoint's console, right? Yeah.
Yep.
Yep. Do you have any similar material on troubleshooting the distributed router?
Yes, as part of the troubleshooting course that I've mentioned, you absolutely cover that, and you can actually come to me, and we can have a quick chat after the session.
Yeah, I mean it's a 2-day course, right? That you guys do, yeah.
Yeah, troubleshooting course is about 3 days of quite in depth. So we obviously can cover it in 1 hour, but yeah, we definitely. So we'll connect after the session, and yes.
The other is that the controller doesn't push the information about the MAC address of the
Correct.
and it is cached locally on the host.
Yes.
But what happens if, for example, the machine is moved via the motion, for example?
Yep.
There will be a certain amount of time for which on this host the information is still in the cache.
Correct. So the question is since VM's moving and the controllers don't actively push MAC addresses onto the host, what happens if the vMotion event happens? Yes, there is a timeout, and I think it's 180 seconds or something like that in a MAC table timeout. So after that, it's just cleared out. What alternatively can happen if vMotion happens and that VM sends a frame to the host, it will overwrite and update the MAC table, so the communication not going to be broken.
So basically,
there is a data path learning as well.
information can be in the cache of multiple hosts. If you remotion the machine and then the machine on the new host send a packet, then there is a way to validate the state information on the cache of all the other hosts.
It's not going to be stale. It's just going to override it with new information. So you had host 1, 2, and 3. You were on a host 1, and your VM was on a host 2, right? And it got moved to host 3. Once it moved to host 3, it sends something back to you. You will know, okay, it's actually pointing to a different VTEP now. Yep. Right. We almost kind of out of time. If you have any more questions, I'm still here. We can continue on. Thank you very much. Thank you.